today's explainer, the mechanics of perpetual symmetry, understanding time crystals. We're going to be exploring a concept that honestly sounds like pure science fiction. It's this strange, entirely new phase of matter that beautifully and kind of elegantly breaks the laws of physics right down to the studs.
Okay, let's dive right into this. I want you to imagine something for a second. What if a clock just ticked forever without a battery? I mean, without any external energy source whatsoever. It just kept ticking, kept moving, infinitely. Sounds like an impossible paradox, right? Like a total glitch in the matrix. But this exact paradox is the core mystery we're unraveling today.
Think of this concept almost like a quantum hourglass. It's essentially a repeating pattern in time, driven entirely by quantum waves. To really wrap your head around this, think about a normal object at its absolute lowest energy state, what physicists call its ground state. Now, normally when a system hits its ground state, it's tapped out. It has literally no more energy to give, so all movement just stops. It becomes completely still. But a time crystal? It represents a system that keeps moving, keeps oscillating forever, even when it's stuck in that absolute lowest energy state. Repeating in space versus time. To really grasp what makes this state of matter so incredibly unique, we need to compare the everyday physical world we all know with this super bizarre quantum reality we're just now discovering. So there's a pretty stark contrast here. Think about normal crystals, like the diamond on a ring, or literally just the salt you sprinkle on your food. Those are highly ordered structures, and they repeat their atomic patterns in normal 3D physical space. But time crystals? They actually repeat their pattern in the fourth dimension, time. They don't just sit there looking pretty. They keep changing, and then they return to their original state periodically, just constantly looping back on themselves in this perfect rhythm.
And this brings us to a really massive, foundational concept in physics called time translation symmetry. This is basically the idea that shifting through time has zero effect on the physical laws themselves. The laws of nature that apply today, they were the exact same yesterday, and they'll be the same tomorrow. A stable object should just remain the same as time ticks by. But, and this is absolutely fascinating, time crystals actually spontaneously break this symmetry. Instead of just sitting static and continuous in time, they self-organize into this robust, periodic pulsing motion. They literally just refuse to sit still. Okay, if that sounds a little dense, let's look at some practical analogies. Imagine you have a pendulum, right? And you hit it with a laser pulse precisely every 1 second. Classically speaking, you'd totally expect it to swing every 1 second, to match. But a time crystal acts like a stubbornly independent pendulum. You push it every second, but the atoms respond by swinging only once every 2 seconds. It essentially just picks its own unique rhythm. Or think of a bowl of Jell-O. Imagine that Jell-O jiggling forever, infinitely, even if you never lay a finger on it, and even when it's cooled all the way down to its absolute lowest energy state. That is exactly how weird and wonderful this whole concept is.
The perpetual motion paradox. Now, I know exactly what you're probably wondering right now. Doesn't this violate, well, pretty much everything we know about thermodynamics? Why isn't this just an impossible perpetual motion machine?
Well, the secret lies in this quote right here. They possess motion without energy. Their apparent motion does not represent conventional kinetic energy. See, time crystals exist in what physicists like to call a crypto-equilibrium. So even though the atoms are constantly moving and oscillating, they actually aren't generating any new entropy. The disorder in the entire system just remains perfectly stationary over time, and because of that, it doesn't actually evade the second law of thermodynamics. It totally respects the boundaries of physics, just in a way we never ever thought was possible.
And here is the real aha moment. You cannot extract energy or work from a time crystal's movement. Since the system is already chilling at its lowest possible energy state, there's simply zero extra energy to give. You couldn't, say, hook up a tiny little gear to a time crystal to generate electricity and power a light bulb. It definitely moves, yes, but the energy in the overall system is perfectly conserved.
A timeline of discovery. Because what's truly staggering here is just how rapidly this mind-bending, seemingly impossible theory transitions straight into a physical, laboratory reality. The story starts incredibly recently, back in 2012, when Nobel laureate Frank Wilczek first theorized the idea of quantized time crystals. And man, it was highly controversial at first. Some papers were even published flat out saying it was fundamentally impossible. But then, fast forward to 2016 and 2017, and two totally independent teams, led by Christopher Monroe and Mikhail Lukin, actually achieved the first physical lab creations.
Then we jump to 2021, and Google creates a time crystal right on their massive Sycamore quantum processor. And incredibly, just recently in 2024, a team at Dortmund University built a time crystal from indium gallium arsenide that hit a 40-minute duration record. To put that into perspective, that is nearly 10 million times longer than previous experiments. So we went from a controversial theory to a 40-minute stable crystal in barely over a single decade. Wild, right?
Real-world quantum applications. So why does all this matter to us? Why are the absolute brightest minds in physics and massive tech giants like Google so incredibly obsessed with this? Let's ground this explainer back in the real world and look at the highly practical, completely future-altering applications of this discovery. Right now, in modern labs, researchers are practically creating these phases of matter. They do things like use lasers to blast a room temperature gas of rubidium atoms, exciting them into this puffy, highly active state. By super carefully controlling those lasers, they literally force the atoms into that repeating time crystalline rhythm we talked about earlier. And doing this allows researchers to deeply explore quantum fluctuations and synchronization, which directly paves the way for some seriously advanced quantum technologies.
The whole crux of why this is such a game changer really comes down to one word: stability. See, quantum computing's absolute biggest, most frustrating problem right now is that qubits, which are the building blocks of these computers, are incredibly fragile. I mean, they are so easily ruined by the tiniest amount of environmental noise or heat, which just causes them to completely lose their quantum state. But a time crystal inherently possesses these extremely stable repeating patterns. It actively resists that environmental noise. It resists just melting into random disorder. This means time crystals could act as the ultimate protective vault for quantum information, potentially serving as the highly stable quantum computer memory we so desperately need to make these machines work. Honestly, they might just be the exact missing puzzle piece to making quantum computers truly reliable. Which leads us straight to the ultimate question we have to ask ourselves as we wrap up today's explainer. How will this impossible phase of matter reshape our technological future? Think about it. We've taken something that literally shouldn't exist, definitively proved that it actually does, and are now looking at it as the key to unlocking the holy grail of quantum computing. We are standing right at the shoreline of an entirely new quantum frontier. Thank you so much for exploring all this with me today, and as always, keep asking those big, seemingly impossible questions.